In this video, I'm going to take you through series circuits containing R and L. That is series circuits containing resistor and an inductor. This video is focused on finding the impedance when you have both resistor and an inductor present in a circuit. So be with me in this class. Watch the video to the end so that you understand every part of the video. This is an AC circuit problem. We have our AC source. In the AC source is connected to a resistor and an inductor at this point. There is a voltage drop here. There is another voltage drop here. So let's see how to find the impedance when you have resistor and an inductor present. From what you have here, this is our source voltage. It's an AC voltage. The total source voltage is equal to the voltage drops here. That is VR plus VL. And this is by Kirchhoff's voltage law. The sum of the voltage drops in any circuit is equal to the total voltage or the supply voltage. So my V is equal to my VR plus VL. When I reach this point, I need to draw the phasor diagram for my VR and my VL. You know that a resistor has opposition effects, and always when you have a resistor, the voltage across a resistor and the current through a resistor, they are in the same phase. So when you are drawing the phasor diagram, the voltage across the resistor will be in the same phase with our current I when you are drawing the I to V. So this is our I here. So let's see. The voltage will take this side. That's the total voltage and this is the current, because the two are not in the same phase when you are considering an AC circuit. In a DC circuit, you realize that our current and our voltage will fall on the same line. Since this is an AC circuit, the current and the voltage will be separated by an angle, which is the phase angle phi. This total voltage has two components, the VR and what? The VL. The VR is in the same phase with the current, that is why it is on the horizontal. Hence, our VL will take this side. So this will be our VL. So this is the phasor diagram for this. The total voltage can be expressed into the voltage across the inductor and the voltage across the resistor. This is a vector notation. Hence, I'm going to have my V squared here. As you know that this VL is also the same as the VL here using vectors. So my V squared will be equal to VR squared plus VL squared. These vectors. Now, you know that the total voltage in an AC circuit is equal to the total current times the impedance, right? And the total voltage across the resistor will be equal to the total current passing through the resistor times the resistance itself. Then we introduce our square here. The voltage across the inductor as well is equal to the current times the inductive reactance, like this. So once we get this equation, our goal is to find the impedance in an RL circuit. So here I'm going to get, I have I here, I have I here, I have I here. So I can divide through by my I squared, by my I squared, by my I squared. Hence I'll be left with Z squared will be equal to R squared plus XL squared. Once I reach here, my impedance is equal to the square root of R squared plus XL squared. So this is equal to the total impedance in a resistor to inductor series circuit. Now let's see this phase angle as we have here. You know that this is our voltage across the inductor, the voltage across the resistor. So if I want to find my theta, that is the phase angle between the voltage and the current in an RL circuit, how do I get it? So in the impedance notation, you can clearly see that my resistor will take this side, then my inductive reactance will take this, provided you have cancelled out the current. Hence, this theta is simply equal to the tan inverse of what my XL over my what R. So my theta is equal to tan inverse of the inductive reactance over the resistance. And this is how we get the phase difference or the phase angle between the voltage and the current in an RL circuit. We just take the tan inverse of the inductive reactance over the resistor. So the current in a series RL circuit, the current in a series RL circuit lags the voltage. So you can see clearly from our diagram that the current lags the voltage, but it's not by 90, but rather an angle theta which you need to calculate for. So in RL circuits, the current I lags the voltage by an angle theta, not 90 degrees. This is the end of this class. Thank you for being with me. See you in the next class. We'll be talking about series circuits containing R and C, resistor and capacitor.